This introduction explores Avi Loeb's concept of the interstellar path to prosperity, examining how the discovery of extraterrestrial technology could foster global peace and scientific advancement through unified human cooperation. The framework centers on how encounters with advanced alien technology might inspire humanity to overcome internal divisions and work together toward common goals, much like how historical threats have strengthened societies. Interstellar objects, such as the anomalous 3I Atlas currently traversing our solar system, represent potential catalysts for this transformation by challenging our understanding of cosmic phenomena and revealing technologies beyond our current capabilities. Ultimately, this path to prosperity hinges on humanity's collective response to external discoveries that transcend our planetary boundaries, potentially leading to unprecedented scientific progress and peaceful global collaboration. Professor Smadar Naoz, a prominent UCLA astrophysicist, expresses a New Year's wish around the Jewish and academic New Year of 2025-2026 for discoveries that promote peace, prosperity, and groundbreaking scientific breakthroughs. This wish perfectly aligns with Avi Loeb's interstellar path to prosperity framework, which posits that encounters with extraterrestrial technology could unite humanity, foster global cooperation, and drive technological innovation that benefits society as a whole. From a psychological perspective, this concept draws on the principle of threat-dependent cooperation, where external threats strengthen group identity and encourage collective action against shared dangers, potentially reducing internal conflicts and geopolitical tensions. The validity of this wish finds support in historical analogies, such as the Cold War space race, which, despite being driven by competition, led to unprecedented technological advancements in communication satellites, medical imaging, and advanced materials that benefited global society. The plausibility of realizing this wish increases with current research on anomalous interstellar objects like 3I Atlas, which exhibits traits that could indicate artificial origins, potentially confirming extraterrestrial technology and inspiring international collaboration on interstellar exploration and sample return missions. Looking forward, if such discoveries are confirmed, they might challenge established models of cosmic evolution while opening new frontiers in energy production, advanced propulsion systems, and astrobiology, ultimately contributing to humanity's collective advancement, prosperity, and lasting peace through shared scientific endeavor. Psychological studies indicate that humans exhibit greater cooperation when confronted with a common external threat. This phenomenon, known as threat-dependent cooperation, draws from research in social psychology showing how shared dangers can strengthen group identity and motivate collective action to protect the group's well-being. Drawing from extensive psychological research, this threat-dependent cooperation works by shifting focus from internal divisions to external challenges. When faced with a perceived threat, individuals are more likely to prioritize group survival over personal conflicts, leading to increased cooperation and unified efforts. In the context of interstellar discoveries, the revelation of alien technology could serve as such a unifying external threat. This shared danger might trigger widespread cooperation, redirecting human efforts toward collective defense and exploration rather than division. By focusing on this external challenge, internal conflicts such as geopolitical tensions or resource disputes could be set aside. The threat-dependent cooperation mechanism suggests that humanity might achieve greater unity and resolve long-standing divisions in response to evidence of extraterrestrial intelligence. 3I Atlas, an interstellar object, exhibits 5 key anomalies that defy standard cometary models. These include its alignment with the solar system's ecliptic plane, its large diameter, its cigar-shaped anti-tail, its nickel-rich composition lacking iron, and its extreme negative polarization. The first anomaly is its alignment with the solar system's ecliptic plane within just 5 degrees. This precise alignment defies the random orbital probabilities expected for natural objects. The second anomaly is its unusually large diameter, reaching up to 46 kilometers. This is significantly larger than typical comets, which are generally under 10 kilometers in size. The third anomaly is its cigar-shaped anti-tail, which appears opposite to the expected direction and is 10 times longer than it is wide. This unusual morphology challenges standard comet models. The fourth anomaly is its nickel-rich composition lacking iron, which resembles industrial alloys rather than the typical iron-rich materials found in natural cosmic objects. The fifth anomaly is its extreme negative polarization with a low inversion angle, which does not align with the expected polarization patterns of typical comets. We will dive into each of these anomalies. The first anomaly of 3I Atlas involves its remarkably close alignment with the solar system's ecliptic plane. This plane represents the flat, disk-like region where all the planets orbit around the Sun, forming the fundamental structure of our solar system. Typically, interstellar objects entering our solar system would arrive from random directions in three-dimensional space. However, 3I Atlas's orbital path aligns closely with this ecliptic plane, deviating by only about 5 degrees from the plane's orientation. This precise alignment of the object's orbital angular momentum vector relative to the Sun is statistically highly improbable for a natural, randomly arriving interstellar visitor. The probability of such a close match occurring by chance alone is less than 1%, based on current observations of only 3 known interstellar objects. This anomaly raises intriguing questions about 3I Atlas's origin. The alignment suggests it may not be a typical natural comet or asteroid, potentially indicating some form of controlled or artificial trajectory that deliberately matches the solar system's primary orbital plane. To properly assess whether this alignment could occur randomly, scientists would need to observe hundreds more interstellar objects. Only with a much larger sample size could we determine if 3I Atlas's ecliptic alignment is an extraordinary coincidence or evidence of non-natural intervention. The second anomaly of 3I Atlas is its unusually large diameter, estimated at up to 46 kilometers. This substantial size sets it apart from most known comets and interstellar objects, which typically have nuclei ranging from just 1 to 10 kilometers in diameter. Larger comet nuclei, while not unheard of, are relatively rare and usually associated with specific types of objects. To visualize this scale, consider that most comets have nuclei measuring between 1 and 10 kilometers across. For example, comet P2005 JQ5 has a nucleus just 1 mile, or about 1.6 kilometers in diameter. Even larger comets like C2014 UN271, which is one of the largest known, measures about 85 miles, or roughly 137 kilometers across. 3I Atlas, at 46 kilometers, falls in between, but is unusually large for an interstellar visitor. This comparison shows comets arranged from smallest to largest. Starting with P25 JQ5 at just 1 mile, we see a progression up to C2014 UN271 at 85 miles. 3I Atlas, with its 46-kilometer diameter, would place it among the larger examples, but still stands out as exceptionally large for an object entering our solar system from interstellar space. For broader context, consider other known celestial objects. For instance, the Black Widow pulsar and various neutron stars and pulsars shown here are typically much smaller, often just kilometers or less in diameter. 3I Atlas, at 46 kilometers, is massive by comparison and suggests it may not follow the patterns of typical cometary bodies. This comprehensive comparison of over 100 comet nuclei shows the range of sizes in our solar system. Objects like 95P Chiron at 271 kilometers are exceptional, but 3I Atlas at 46 kilometers is still remarkably large for an interstellar intruder. Its size adds to the mystery, making it harder to explain through conventional cometary models. This substantial size further distinguishes 3I Atlas from conventional interstellar objects and adds to the mystery surrounding its origin. Its significant size makes it more difficult to explain its features through natural cometary processes alone, suggesting we may be dealing with something truly anomalous in our understanding of interstellar visitors. The third anomaly of 3I Atlas is its cigar-shaped anti-tail. Unlike typical comets that have tails extending away from the Sun due to solar radiation pressure and solar wind, this object features a tail that points directly toward the Sun. This anti-tail is composed of scattered sunlight reflecting off dust particles in a narrow, elongated shape that is 10 times longer than it is wide. Such characteristics are extremely rare in cometary bodies and challenge our understanding of how comets behave in the solar system. The fourth anomaly of 3 Atlas involves its unusual elemental composition. Spectroscopy reveals that this interstellar object is nickel-rich but notably iron-poor, a composition that closely resembles industrially produced nickel alloys used in human manufacturing. This chemical signature stands in stark contrast to typical cometary bodies, which are generally iron-rich with iron as a dominant element in their makeup. The absence of significant iron content in 3I Atlas challenges our understanding of natural cometary formation and raises intriguing questions about whether this object might have an artificial origin, perhaps constructed or modified by an advanced extraterrestrial civilization. The fifth anomaly of 3I Atlas involves its extreme negative polarization and low inversion angle. To understand this, we need to explore how light polarization works in astronomy. When sunlight scatters off dust particles in space, the light becomes polarized. This means the electromagnetic waves align in specific directions rather than being randomly oriented. Polarization can be positive or negative. Positive polarization occurs when light waves are parallel to the scattering plane, while negative polarization happens when they're perpendicular. Most natural objects show positive polarization at small scattering angles. The inversion angle is the critical scattering angle where polarization switches from positive to negative. For most natural celestial bodies, this inversion occurs at angles around 20 to 30 degrees. 3I Atlas exhibits extreme negative polarization and an unusually low inversion angle. These properties are highly uncommon for natural celestial bodies like comets or asteroids. Natural comets typically show positive polarization at small scattering angles, with inversion angles around 20 to 30 degrees and gradual changes in polarization behavior. 3I Atlas's extreme negative polarization and low inversion angle defy these patterns. This peculiar polarization behavior further distinguishes 3I Atlas from typical natural objects and strongly suggests the need for additional investigation into its true nature. The Loeb scale is a conceptual framework developed by astrophysicist Avi Loeb to evaluate the origins of interstellar objects like 3 Atlas. This scale helps distinguish between natural cosmic bodies and potential technological artifacts from extraterrestrial civilizations. At one end of the scale lies natural origins, characterized by objects that behave like typical comets or asteroids. These exhibit gravitational trajectories, mass shedding, and compositions consistent with solar system formation. At the opposite end sits technological origins, where evidence of artificial design becomes apparent. Evidence tilting toward natural origins includes comet-like behavior, such as mass shedding, icy compositions, and random trajectories following gravitational laws. Technological indicators would include artificial electromagnetic signals, controlled maneuvers defying gravity, or materials and structures beyond natural processes. For 3I Atlas, the 5 observed anomalies make its position on the Loeb scale particularly intriguing. Data from upcoming observations will be crucial in determining whether this object represents a natural interstellar visitor or something more extraordinary. Observations from Mars orbiters in October 2025 and Juno spacecraft in March 2026 will provide high-resolution data on the object's behavior, composition, and potential maneuvers. This information will help scientists definitively place 3I Atlas on the Loeb scale, potentially revealing whether humanity has encountered its first technological messenger from another star system. Upcoming observations from Mars orbiters on October 3rd, 2025, and Jupiter's Juno spacecraft on March 16th, 2026, will provide critical data about 3I Atlas. The Mars orbiters will capture high-resolution images as the object passes within 29 million kilometers, potentially revealing whether it has a small kilometer-scale cometary nucleus or exhibits artificial electromagnetic signals beyond natural reflections. The Juno spacecraft will gather additional data when 3I Atlas approaches within 54 million kilometers of Jupiter, allowing scientists to detect any significant deviations from purely gravitational orbital paths that might indicate artificial maneuvers or non-natural propulsion. Together, these observations could provide the definitive evidence needed to determine whether 3I Atlas is a natural interstellar comet or a technological artifact from another civilization. A velocity shift of 30 to 40 kilometers per second during October 2025 could bring 3I Atlas, or a component of it, to Earth between December 26, 2025, and January 9th, 2026. Such a velocity change is within the capabilities of our own rocket technology, raising the possibility of non-gravitational forces acting upon the object. David O'Neill, a retired technology executive and amateur astronomer, raises important questions about the statistical significance of the anomalies given the small sample size of observed interstellar objects. With only 3 known interstellar visitors, Oumuamua, Borisov, and 3I Atlas, O'Neill highlights the risk of overstating coincidences when drawing conclusions from such limited data. He questions the point at which we should consider more exotic interpretations for the observed physical anomalies, such as when natural explanations become statistically improbable. Avi Loeb counters that while probabilities demand more data, the low likelihood of random alignments within 5 degrees of the ecliptic plane, less than 1%, makes these anomalies meaningful and worthy of investigation. This debate underscores the tension between scientific caution and curiosity in exploring potentially groundbreaking discoveries. The statistical concerns raised about small sample sizes are valid, given that humanity has observed only 3 interstellar objects so far: Oumuamua, Borisov, and 3 Atlas. However, the probability calculations reveal compelling evidence that warrants deeper examination. With just these 3 observations, statistical analysis shows that the chance of an object like 3I Atlas aligning so closely with the solar system's ecliptic plane, within just 5 degrees, is less than 1% for random directions alone. When factoring in the additional improbability of its trajectory timing, passing near Mars orbiters in October 2025 and approaching Jupiter's Juno spacecraft in March 2026, the statistical significance becomes even more pronounced, dropping to tiny probabilities that challenge pure coincidence. Despite the limited sample size, these specific coincidences strongly suggest that the anomalies observed in 3I Atlas may represent more than mere random occurrences in the vastness of space. This compelling evidence justifies the need for continued observation and further investigation to determine whether these patterns indicate something extraordinary about interstellar visitors. Avi Loeb criticizes dogmatists in science who suppress imaginative thinking and alternative interpretations. He calls out the thought police who dismiss speculative ideas without proper investigation, hindering scientific progress. Dogmatism creates a divided world where open-minded inquiry is suppressed. The book Divided, Open-Mindedness and Dogmatism in a Polarized World illustrates how rigid thinking polarizes scientific communities, preventing the exploration of new ideas. Scientific dogma refers to rigidly held beliefs that limit exploration. In molecular biology, as shown here, established models of DNA replication can overlook anomalies. When replication is misregulated, it causes diseases, demonstrating how dogma hinders understanding and innovation. Confirmation bias exacerbates dogmatism by causing scientists to overvalue evidence that fits their beliefs while undervaluing contradictory facts. This prejudice can prevent objective analysis, particularly with anomalies like those of 3 Atlas. For 3I Atlas, prejudice against alternative explanations could hinder our ability to uncover the truth. Loeb emphasizes that open-minded inquiry, challenging dogmas, and embracing imagination are essential for scientific advancement and understanding the mysteries of the universe. Even if 3I Atlas turns out to be a natural comet rather than an artificial probe, its interstellar origin alone makes it scientifically invaluable. As one of only a handful of known objects from outside our solar system, it represents a unique opportunity to study materials that have formed in entirely different cosmic environments. Future space missions could be designed to intercept objects like 3I Atlas, collect physical samples from their surfaces or comas, and return these samples to Earth for comprehensive laboratory analysis. This type of sample return mission, similar to OSIRIS-REx but targeting interstellar visitors, would open up new frontiers in astrobiology and planetary science. Once back in laboratories, scientists could analyze the chemical composition, mineral structure, and isotopic ratios of these materials in ways that are impossible with remote observations alone. This detailed analysis would reveal how planetary systems form under different conditions, providing insights into the processes that shaped other stars and their orbiting worlds. Beyond planetary formation, these samples could contain the chemical building blocks of life, such as complex organic molecules, amino acids, or even primitive biological precursors. Studying these extraterrestrial materials would help determine whether the conditions for life are universal or unique to our solar system, advancing our understanding of life's origins across the cosmos. Ultimately, the scientific value of natural interstellar objects like 3 Atlas lies in their potential to expand our knowledge of cosmic diversity. By studying these visitors, we gain a broader perspective on the universe, from the mechanics of star and planet formation to the fundamental chemistry that makes life possible. The OSIRIS-REx mission, launched by NASA in September 2016, represents a landmark achievement in planetary science. This spacecraft was designed to study the near-Earth asteroid Bennu, a potentially hazardous object about 500 meters in diameter, and return pristine samples of its surface material to Earth for detailed laboratory analysis. Bennu, officially designated 101955 Bennu, was discovered in 1999 and named after an ancient Egyptian bird deity. This B-type asteroid has a primitive carbonaceous chondrite composition, meaning it contains organic materials that have remained largely unchanged since the solar system's formation over 4.6 billion years ago. The mission's detailed imaging revealed Bennu's rough, boulder-covered surface and its surprising activity, including particle ejections. The mission's most critical phase occurred on October 20, 2020, when OSIRIS-REx performed a precise touch-and-go sample collection maneuver. The spacecraft briefly contacted Bennu's surface for just 16 seconds, using its robotic arm to fire a burst of nitrogen gas that stirred up and captured surface material. This innovative technique collected an unprecedented 121.6 grams of pristine asteroid regolith, far exceeding the minimum requirement of 60 grams. The sample capsule safely returned to Earth on September 24, 2023, landing in the Utah desert. Preliminary analysis of the returned samples has yielded groundbreaking discoveries. Scientists identified several organic compounds, including amino acids such as glycine and beta-alanine. These molecules are fundamental building blocks of proteins and life as we know it. While amino acids have been found in meteorites before, their detection in samples from Bennu provides direct evidence of prebiotic chemistry in the asteroid belt. This finding enhances our understanding of how life's ingredients may have been delivered to early Earth through asteroid impacts. The OSIRIS-REx mission's success establishes a critical precedent for sample return missions from small celestial bodies. It proves that we can safely navigate to, collect from, and return pristine samples from asteroids, overcoming challenges like low gravity, unknown surface conditions, and the vast distances involved. This technical achievement opens the door to similar missions targeting interstellar objects like 3 Atlas, which could provide unprecedented insights into planetary formation beyond our solar system and potentially reveal biosignatures or even technological artifacts from other civilizations. Avi Loeb draws a compelling parallel to Galileo Galilei, the pioneering astronomer who faced intense opposition for challenging the established geocentric model of the universe. In the early 17th century, the dominant view held that Earth was the stationary center of the cosmos, with the sun and planets orbiting around it. This geocentric model was not just scientific theory, it was reinforced by religious and philosophical authority. The geocentric model, widely accepted for centuries, placed Earth at the center. Celestial bodies like the sun, moon, and planets were believed to revolve around our planet in perfect circles. This view aligned with biblical interpretations and Aristotelian philosophy, making it dogma rather than hypothesis. Galileo challenged this with his observations through the telescope, supporting the heliocentric model proposed by Copernicus. In this revolutionary view, The Sun occupied the central position, with Earth and other planets orbiting around it. This shift wasn't merely astronomical, it undermined the human centric worldview embedded in society. Galileo's advocacy for heliocentrism brought him into direct conflict with the Catholic Church and prevailing authorities. His telescopic evidence, such as Jupiter's moons and Venus's phases, provided empirical support for the sun-centered model. Yet, in 1616, the Church declared heliocentrism heretical. Galileo was tried by the Roman Inquisition in 1633, forced to recant his views, and placed under house arrest for the rest of his life. Loeb uses Galileo's story to illustrate the perils of dogmatic authority in science. Even when evidence mounts against established views, powerful institutions can suppress innovative ideas. Galileo showed that independent reasoning and empirical observation must prevail over popular opinion or enforced dogma. The lesson for modern science is clear. Popular views can sometimes be wrong, and questioning authority is essential for progress. Just as Galileo faced ridicule and persecution, today's scientists must challenge prevailing paradigms to uncover truth. This principle applies to interstellar anomalies like 3I Atlas, where open inquiry trumps dogmatic dismissal. Encountering alien technology could spark major breakthroughs in various fields, including energy, propulsion, and materials science. This infusion of new knowledge and capabilities could propel humanity forward, similar to the paradigm shifts triggered by technologies developed during the space race. In energy, we might discover advanced power sources that go beyond fossil fuels or current nuclear methods. Propulsion could revolutionize travel and exploration, enabling faster or more efficient space journeys. Material science would benefit from lighter, stronger substances for everything from spacecraft to everyday construction. This parallels the technological advancements from the space race between the USSR and USA, where competition drove innovations like satellite communications, medical imaging, and computing that transformed daily life. Building on current spacecraft components, with their mechanical and electrical elements, such breakthroughs could be integrated into our existing technology base, creating a foundation for future progress. These discoveries could create paradigm shifts, fundamentally changing how we approach science and engineering, and inspire cascading new discoveries that build upon each other for generations to come. The confirmation of extraterrestrial intelligence could have a profound impact on global politics, potentially reducing geopolitical tensions and fostering a sense of shared identity and purpose among humanity. Just as the Cold War threat spurred cooperation, an alien encounter could unite us against a common cosmic challenge. The ability to routinely collect samples from interstellar objects, like 3 Atlas, would revolutionize astrobiology. By bringing back physical materials from these distant visitors, scientists could directly analyze their composition, searching for signs of life's building blocks, such as amino acids and other organic molecules. This direct sampling would go far beyond remote telescopic observations, providing unprecedented data about the chemistry and potential for life beyond our solar system. Such sample collection would open entirely new frontiers in our understanding of the universe. Interstellar objects could reveal how planets form in other star systems, challenging or confirming our current models of cosmic evolution. The data might show whether the processes that created life on Earth are universal, or if our planet's development was exceptionally rare. This capability builds on successful missions like OSIRIS-REx, which collected samples from asteroid Bennu and found evidence of life's precursors. Applied to interstellar objects, it could transform astrobiology from a field of speculation into one grounded in direct evidence, potentially answering fundamental questions about life's prevalence in the cosmos. Moreover, studying these samples could provide new insights into our own world. By comparing interstellar materials with those from our solar system, scientists might better understand Earth's unique position and the processes that made life possible here. This comparative analysis could reveal whether Earth was shaped by common cosmic events or exceptional circumstances. The mystery of 3I Atlas remains unsolved, but the upcoming data from Mars orbiters and the Juno spacecraft hold the key to its true nature. These observations will provide high-resolution imaging and trajectory analysis that could reveal whether this object is a natural comet shedding mass or something exhibiting artificial maneuvers. Mars orbiters, such as the 2001 Mars Odyssey, will get a close look at 3I Atlas on October 3, 2025, when it passes within 29 million kilometers. This will allow for detailed assessment of its nucleus size, potentially confirming if it's less than 1 kilometer, and its mass shedding behavior, which could indicate natural cometary activity. Additionally, the Juno spacecraft orbiting Jupiter will have its turn on March 16, 2026, approaching within 54 million kilometers. This observation will help confirm or refute the potential velocity shifts and non-gravitational forces that could indicate artificial propulsion. Whether 3I Atlas turns out to be a natural comet, offering valuable astrobiological insights into the building blocks of life, or a technological messenger from another civilization, prompting revolutionary advancements in science and technology, it challenges us to embrace curiosity, question dogma, and remain open to the profound possibilities that lie beyond our solar system. Just as past missions like New Horizons have expanded our understanding, this object could redefine our place in the cosmos. Only with patience can we be sure. As we await the definitive data from these upcoming observations, we must maintain an open-minded approach to scientific inquiry, recognizing that the greatest discoveries often come from questioning what we think we know.